Good morning, everyone. Welcome to day 10 of HSMA. We're going to be going through facility location problems today. This is carrying on from last week where we went through the Python mapping elements. So we're going to be working in Python today, working out if I've got a certain number of facilities, where should I put them? Or if I want to close a facility, which one should I close to be the most equitable from a travel time perspective, and so on. So hopefully this will be an exciting day. We will, if we've got time, go back to the bit that I had to lop off the end of session 3C last week on getting travel times from web services yourself. So without any further ado, let's kick off. So facility location problems. Now, one of your jobs as a data scientist within your organization, as an analyst within your organization, is to help your organizations make decisions when it comes to where should I put my services. So in real life, this may actually look at reviewing and rationalizing whether existing service locations are the best ones that exist, providing a comparison of the different pros and cons of proposed sites for a service. So if we've been provided with 5 new places we could put this service based on the buildings available, etc. Is it a good place based on staff travel times? Is it a good place based on patient travel times, and so on? And also suggesting optimal locations for new services if there are existing inequalities or areas of poor access. You might not have a hypothetical location in mind for the service. You may need to provide an idea of roughly where should a service be located to best address prior inequalities. You might also find yourself in a situation where you have services that need to be amalgamated, services that need to be closed due to limited budget, etc. And it may be that you can provide support to make sure that the service that is closed down is the one that will have the least impact on access and equality across your service users. So facility location in healthcare, this is, it's a problem that exists and is very commonly done for, issues outside of healthcare. If you've got a series of, if you're a restaurant chain, you want to work out where should I put my new restaurant chain to maximize my profit. Great. You can use a facility location algorithm for that. But in healthcare, it really makes the most difference. If your facilities are not utilized well, then it's going to have a major impact on public health. It's going to have a major impact on individuals. Facility location is crucial in healthcare problems. So I'm going to take you through a real world example quickly. The project aimed, in this case, to assist in planning sexual health services in Hampshire. This was done by a couple of people, but also including one person from our Pencord team. This work has inspired some of the code, etc., that you will be seeing today. But yeah, this project was looking at sexual health service provision in Hampshire. They were forecasting future demand for different parts of the service over the next 3 to 5 years. So this was the first stage of the project. So bringing in these demographic projections, which can be a really crucial part of your facility location problem. So not an essential one, not one that you have to do for every problem, but it's great to know that you can go away and look at these sort of demand projections, potentially using some of the skills we'll teach later in the course as well. They were then performing a facility location analysis based on the current and forecasted demand to work out what the optimal number of clinics be and where should they be placed. So in this case, they were aiming to reduce the number of clinics that were available whilst also maintaining or potentially even improving access to services. So in this case, they had 28 existing clinics. They needed to know which ones should be kept open. And they also had a second scenario. If they had these 28 existing clinic locations or any other potential location within Hampshire based on, one potential location per postcode sector they used in this case, where should they be putting these clinics? So that was 305 potential locations to put a clinic. 28 clinics were their kind of budget of clinics. And in both cases, they were interested in people potentially being able to get there in 30 minutes on public transport and 15 minutes of driving. So quite a complex problem. You can see that we can bring in multiple aspects of travel times. We can bring in multiple aspects of where the services can be located to build up quite an elaborate problem statement. So as well, we have demand points. So not just where could our services be placed, we also need to think about where could people be coming from and how can we partition that up in a way that makes sense to a computer, in a way that is useful for us when we're trying to code these problems. So in this case, they had postcode sectors. You could be looking at lower super output areas, middle layer super output areas. So these LSOAs and MSOAs that we've talked about, you could be looking at, the postcode to the level of, say, EX5, EX6, EX7, that sort of first half of it, or you can take it a little bit further to include the first number that comes after generally the gap in your postcode. And that gives you a slightly higher level of resolution. So in this case, that's what they were doing. They were looking at these postcode sectors, the 278 places that patients could effectively be coming from, and going to any of these 28 hypothetical clinics. But what combination of this 28 hypothetical clinic locations? In this case, they found that actually you only needed 20 facilities to allow public transport travel targets to be met for 90% of the population. They didn't need the 28 that were previously there. However, meeting travel time target for 100% of the population would then require an additional 5 facilities. And you can start to get into that question of, is that trade-off worth it? For that sort of fairly marginal gain at that point? You've made a very big impact, got your 90% of people in to the travel time targets through 20 services. Is 25 services actually worth it to get that final 10%? That's a question for your stakeholders, and that's where you're providing this sort of value, this decision support, by showing them these different parts of the solution. Now, actually, if you just say that instead of for the car travel times, you only need 14 clinics to achieve a 99% of coverage in this problem for being able to drive to a clinic in 15 minutes. And actually, if you relax your parameters to, well, what about within 20 minutes? Then yeah, with these 14 clinics, you could get people within, you could get your entire population able to drive to a clinic within 20 minutes. So they found, in summary, that the clinic locations could be reduced from 28 to 20. You could still keep 90% of all patient journeys by public transport to a clinic within 30 minutes. And actually, if you did it within travel times, you could reduce it even further. The public transport analysis did, however, assume that everyone would travel by public transport if that was, they therefore looked at just public transport for that section, but this is quite unrealistic, thinking about people, the majority of people in that county did have access to cars, but starting to think then about, does that match up with your demographic who are likely to use this clinic? It can all get quite complex. This is why, a location allocation problem can be your entire project very comfortably, bringing in all these different aspects and thinking about how best to deal with them within code. And often you will find that you get diminishing returns with more and more clinics. So where we were talking about the fact that 20% of clinics were going to get you most of your demand coverage. So here we're looking across our x-axis at 20 locations, read up, read across, and actually 90% of demand, the sort of goal travel time was covered with 20 clinics. And actually then from there on, you're seeing that it's taking a long time to get much further up than that. So it really is worth kind of looking at these when you've got these sort of more flexible problems with a number of clinics that could be covered. How do you start to build up to that? So hopefully that's a nice real world example that shows these sorts of analysis can be really powerful for optimizing the use of healthcare resources. We've taken away effectively redundant clinics. It's all a little bit more complex than that. Obviously, I'm oversimplifying. How do you define exactly that clinic isn't good in some other way? Is there a certain amount of specialization there? How are we going to redistribute that? How does this affect the teams that are based in those in those clinics? But actually, from a purely sort of travel time perspective, the aspect that you're going to be looking at primarily as an analyst, you'll be providing that decision support, saying, well, logically, this is the best solution, or these are the best possible solutions. And your stakeholders will then be going away and going, okay, well, here's our knowledge around this area and why one of these solutions might be better than the other. But how do we actually go about formulating these problems? How do we go about translating this location allocation problem into code and running this ourselves? Well, the first thing we need to think about is whether our demand is discrete or continuous. Our locations are discrete and continuous. So what we teach on this course is what's called discrete modeling of location allocation problems. This assumes that that demand can be aggregated to a number of discrete points. So rather than going, well, everyone will be coming from a very slightly different point in their LSOA, in their MSOA, in their postcode. Actually, we just assume most of the time that they're coming from the center of that LSOA or postcode, rather than having to work out an almost infinite number of travel times, not quite infinite, but you get what I mean. You can simplify this down to a couple of hundred locations to work from. This also assumes that there is a finite set of candidate locations where facilities will be placed. So again, rather than trying to optimize to the exact kind of very precise latitude and longitude where you would ideally place a candidate, instead we provide candidate locations, whether that's, oh, we've got 5 possible sites in mind and this is where they are, or whether it's something a little bit more like the problem I just talked about, where they said, well, we could put these clinics within any one of these 278 central points, the center of our postcode sectors, and that's a good enough approximation for us to then start working from. The alternative is continuous, as I say, where locations can basically be anywhere within a range, and we don't cover this in the course. It's a much more complicated thing to try and work out in the kind of problems you're working with, not really much benefit. Then there's a couple of different ways that we can start to think about the problem. We cover in this course what's called the p-median problem, but it's worth knowing about what we call the location set covering problem and the maximal covering location problem. Feel like those names are a little bit more unfriendly than the actual concepts they're trying to convey, so I'll go through them one by one. The p-median problem is basically, I want to place a certain number of facilities to minimize the overall travel time of everyone who might want to access the service. So if I've got lots of people coming from somewhere in particular, I also want to take that into account. So if I've got my my region, but I know that my service users tend to be older, and I know that my service users historically, therefore, will be in a particular area, most likely coming from there, I want to take that into account. I don't want to weight every possible region that people could be coming from the same. I want to have I want the actual likely demand to have some sort of bearing on my final output. You can also simplify it down within a p-median problem and say, well, let's assume that the demand is going to be equal from every possible location. So you can do that, but generally you'll be looking at these weighted travel times and actually say, which we'll go through in a second, and saying, right, I care more about the people that have come from this area, or it might be that people from more or less deprived areas tend to use the service more. It might be there might be some historical precedent that you can bring in, some historical data on the service access. Always be a little bit careful with that as well, depending on the kind of service it is. That might be a little bit biased. It could be reflecting the historical difficulties in accessing that service. So, do take that with a pinch of salt. But effectively, we're trying to find a way to account for this variation in demand in a way that makes our final outcome fairer. Now, the ones we don't cover, but absolutely you could look into doing in your own project if this is the kind of thing that makes sense for your services and your project. The location set covering problem. So this is where you might want to say, I don't care how many services I place. It is absolutely essential that everyone needs to be able to access this service within a certain period of time. So for example, an accident and emergency department or a minor injury unit, you might want to say, doesn't matter how many of these I need, people need to be able to get to one of these within 15 minutes or 20 minutes, something like that. Then you have the maximal covering location problem. And this is where you still have a sort of defined number of facilities. Say you've got the budget for 6 clinics, and you want to place them so that as many people as possible can get to the service within a certain time. So it's slightly different to this p-median problem. We're not just trying to minimize the travel time for everyone. We're trying to maximize the number of people who can access it within a certain time cutoff. So actually, let's say, if we put this configuration of services, then 90% of people can access the service within 30 minutes or less. If we move the configuration of services around, then only 85% of people can access the service in 30 minutes or less. Might be that the weighted travel time, taking into account those people further away, is better. So it's, in the second example, where we weren't maximizing the number of people who could access the service in 30 minutes. So it depends what your stakeholders value, what is important for the kind of service you're working with. As I say, in this session, we will be focusing on the p-median problem, but it's useful to know the other kinds of problems so that you can go out when you get to your project, look at the literature, talk to me and Dan, talk to other people in the community about how you might go about those kinds of problems. So, bit of a summary of that there. I won't go back through that again, but it's in the slides for you to refer back to. So as I say, we're going on to the p-median problem now. A p-median problem is just one where we care about locating p services. So p in this case is referring to the number of services. That could be 1 service, 2 service, 5 service, 25 services, however many services you are interested in, and you are trying to minimize the weighted average travel time or potentially the weighted average distance of users in some way. So overall, how can we minimize the travel time on average that people will be spending to get to the service? So let's assume we've got a hospital down here in Cornwall, Penzance actually, so we're pretty far right down the end. Now let's think about this person over here. They've got a journey that takes them 10 minutes to get from this little section on the coast to this hypothetical hospital. If we look at this person over here, journey B, their journey takes 30 minutes. If we just take a simple average of those two, then we can say that on average, it's going to take 20 minutes for someone to drive to this hospital. We take 10 minutes over here, we take 30 minutes over here, we add them together, we divide them by the number of journeys in this case. So we've got 10 plus 30 divided by 2, average of 20 minutes. But what if lots of people live in this area? In this case, it's St. Just, and do journey A, but only one person lives all the way over here and does journey B. Because if we just looked at this and said, well, okay, that journey takes 10 minutes and this journey takes 30 minutes. Well, let's move the hospital a little bit further over here so it's fairer for everyone. Everyone's then got an average travel time of, let's say, 15 minutes or a little bit more. Dan saying in the chat, not a lot of people live in St. Just. But if we've got the travel time here, then actually what you'll find is, maybe that's what you want to change. You want to move it over because that feels fairer. But let's assume lots of people do live in St. Just and do journey A and only one's living over in Sydney and doing journey B. Well, now we can start to weight the travel time. We've got 5 people over here doing this journey. So 10 minutes times 5 is 50. Over here, we've got the 30-minute journey, but only one person is doing it. We then add up these new numbers. So we've got 50 plus 30 is 80. Our weighted average at this point is only 13.3 minutes. What if we swap that round? What if the 5 people actually live over here in Sydney and only one person is coming from St. Just? Well, this time our weighted average will be, we've got one person doing this 10-minute journey, so that's 10. We've got 5 people doing this 30-minute journey, that's 150, 30 minutes times 5. Add those two together and you've got 160. Take this, divide this by the average number of trips, the total number of people in this case, and you've got 26.6 minutes. So depending on the demand here, your hospital location hasn't changed, but your judgment of how good this solution is has changed quite significantly. So if this is what the distribution was, this might not be such a good location for the hospital, but if this is what the distribution is, it's a pretty good location for the hospital, it seems. So yeah, comparing this across the two, we can see that we have quite a significant difference in our weighted average travel time. Now, one thing to keep in mind with this is it doesn't look at the maximum travel time. Certain services, like your accident and emergency services, your stroke units, anything else where it's really important to get to a service within a certain length of time, you might not be so concerned about minimizing the average length. You may, as we've talked about with the other kinds of problems, be worrying about, can everyone within your catchment area be a certain number of miles or minutes away from the service? You can still look at this within the p-median problem. So when we go into the exercise and go through the code in a minute as well, you'll see that we do look at the maximum travel times as well. So it's not just a case of, well, we've only worked out the weighted travel times, that's all we can provide to your stakeholders. With the way we structure the problem, the way we structure the code, you can pull back these maximum travel times as well. You can see these edge cases and start to go, well, okay, maybe this is the best solution from a weighted travel time perspective, but this second best solution actually means we haven't got so many people with these really long travel times, our sort of edge cases. So just focusing on the weighted average travel time sometimes could lead to a slightly inequitable solution. So as I say, we've also got the location set covering problem, maximum location problem. We won't go through these now, but effectively going back over these now, you've had a little bit of time to look at the weighted problem. Location set is what's the minimum number of facilities and where should they go so that everyone has at least one facility within a given maximum distance or time. The maximal covering location problem, how can we locate the facilities in such a way that as few people as possible do have a service within target distance or time. Sorry, there was a typo on that slide. The other thing that is worth noting with the maximal covering location problem is if you can't cover all demands in that way because it's too expensive to do so, it tries to maximize it for areas that generate lots of demand rather than those that generate less. So it's still kind of weighted in a way. So as I say, in reality, you might care about all of these to some extent. Your best solution to the P-median problem has a really long maximum travel time. So it is just important to make sure you're presenting this to your stakeholders. It can be really crucial to help them make an informed, fair and safe decision about this problem. And there's lots of different ways you can provide this. We'll go through a few different ways, but a simple table with potentially a couple of rankings of your solutions can go a long way. So actually you could be looking at something like, here's my different possible combinations of clinic locations. This is the best solution in terms of average weighted travel time. If we take the weighting out of it, it's also the best solution from a simple average perspective, and it's also the best solution from a maximum travel time perspective. So we've just looked at all of the different outputs from this solution and gone, right, this is the best, this is the second best, this is the third best, and so on. And we've ranked it based on each of these different measures. And then we can actually start to add up these ranks and give you a little bit of an idea of, well, even though we've ordered this particular table by the average weighted travel time, we've got the one with the lowest average weighted travel time first, the second lowest second, and so on. If you look at this one across all of the different things that we're measuring, it's not actually the second best. It drops down the table quite significantly. This is a sum of the ranks. You know, it's quite a simplistic way of looking at it, but it does help you to start to think through what different things might affect whether this is a good solution. How do you define a good solution, and how do you give your stakeholders the information they need to judge whether this is a good solution? Because they also might look at your very first solution and go, well, that's not going to work because the SACH hospital is actually a recognised centre of excellence, and we know that that's a team we want to keep together. So we can eliminate this solution off the bat. If you'd only given them the best solution, well, suddenly your analysis is useless to them. So as I say, keep saying we focus on the P-median problem in this course. So how do we actually start to turn this into code? Well, most of the time you'll probably start with a series of known locations for services. These will either be the proposed locations for the services. So it might be that that you've got a range of possibilities based on buildings that are owned by the organisation, areas with buildings available for rent, and so on. Before you, so you've actually received a sort of list of possibilities from someone. It might be that there is more flexibility. So actually, as we said before, allowing the centroid of each LSOA, each postcode, etc., to be a possible location. And it might be that you're then going back to people and saying, well, this is where we think it would be best to place their service. And then they go away and go, well, is this actually feasible? Do we have some space there? Do we have a building for rent in this area? It might just be the locations of all of your existing services. So it might be that there are already services available, and it might be a mix of the two. So you could have all of your existing services, and you might be looking to add one more service or take away a service. So you will have some combination of service locations. That's what you need. You need latitude and longitude of where are these services located. You will also need a travel matrix. So you need the sources of demand as rows. So where will people be traveling from? Every time we talk about a source throughout this session, we're talking about the place that people live, or whether, if it's not live, that they will be traveling from. So these will be our rows. Our LSOAs generally will be working with throughout today, but these could be, again, postcodes, it could be MSOAs. It depends how detailed you need to go. If you're doing a location problem that looks at the entire country, A, you're going to run into some other problems, we'll talk about that later, but B, you might actually go, well, let's just look at MSOA level. Otherwise, we're going to have tens of thousands of LSOAs to look at, and actually looking at MSOA makes our life a bit easier. If you're focusing in on a very small region, then maybe you want to look at postcode sectors instead. But LSOA is a nice sort of middle ground for us to start from for these exercises. Now, the destination, so every time we talk about a destination in this session, we're talking about possible clinic locations. So these will be our columns. So every time we sort of read across them, we go, okay, to travel from LSOA 1 to possible site location 1, it's going to take, in this case, 23.7 minutes. To get from LSOA 1 to possible site location 2, it's going to take longer, 26.2 minutes. LSOA 4 to site location 4, we read across from here, down from here, 28.2 minutes to get to that site location from this LSOA. So this will hopefully feel a little bit familiar from what we were doing in the last session. And hopefully that will make you see why that was worth doing as well. So these travel times, or potentially distances, this could be miles instead. That's absolutely a valid way of looking at it, but travel times do bring their own raft of benefits. So these are our travel matrices from the last session. So when we did our travel maps before, all we were doing to visualize them was working out the shortest possible distance within for each LSOA. So we wanted to color each LSOA by the shortest possible time it would take to get to one of these hospitals. So we were maybe looking at just existing hospitals and going, right, okay, are there any sort of areas where we're not seeing such good access? So we see in places where there's a particularly long travel time and visually going, well, maybe I want to put a service there. Is that the best choice? Don't know. That's what this can help solve, but we're still going to be needing to work out the shortest possible distance to actually calculate the best locations for these hospitals and the best combination of locations. So if we've got 4 possible sites, again, we'll just be reading across and going, okay, from LSOA 1, okay, the shortest location, the shortest travel time is this one here, site location 3. Let's put that into our shortest column. LSOA 2, up 14.2, same site actually, but this one here, LSOA 3, the shortest possible travel time is 18.7 to site 4. So that's what goes into our new column that we've created called shortest. In reality, we'll get pandas to do this for us. We won't be manually calculating this for every LSOA. But now what we're changing is which clinics are available. So as we go through our Python code, what we'll be doing is chopping out a couple of these columns effectively. So instead of having sites 1, 2, 3, 4, we'll maybe only have sites 1 and 3. This time when we read across 19.1, 14.2, 21.3, so LSOA 3 this time, shortest travel time is 21.3 minutes. Go back to here, LSOA 3, well, we don't have this site location 4, which was our previous shortest time. So now the shortest travel time has to be different. And if you have a different combination of possible sites, then we will have a different shortest travel time. What we then need to do is go through and represent these as an integer array. So let's say we currently have 4 locations that we're delivering routine health screenings from. Due to constraints, we're going to have to cut this down to 3. So we've got 4 practices: Leafy Lane practice, Cactus Heights surgery, Flowerpot Road practice, and Sunny Mountain surgery. How can we turn these practices into something that Python can understand and give us all the possible combinations of? So what are the possible combinations for a start of these 3 practices if we sit down and work this out? Well, or taking 4 practices and only returning 3 of them. Well, we have only 4 possible outcomes. So in this case, the order doesn't matter. It's important to notice that it doesn't matter if we've got Leafy Lane, Cactus Heights, and Flowerpot, or Leafy Lane, Flowerpot, Cactus. That's exactly the same in this situation. In some kinds of problems, that wouldn't be the same, but not in a geographic location problem. The order of the services doesn't make a difference. So 4 possible sites, in this case, 4 possible combinations of 3 surgeries. Now, again, how do we turn this into something that Python can do for us instead? Let's give each of our practices a numeric ID. So remembering Python starts from 0, we have Leafy Lane practice as 0, Cactus Heights is now 1, Flowerpot is represented by 2, and Sunny Mountain is represented by 3. And now it's a little bit easier to start looking at what our outputs in Python would be. So this combination will be represented as 0, 1, 2, and it wouldn't have this 3 in. Then we have 0, 1, 3, 0, 2, 3, and 1, 2, 3. Those are all the possible combinations. And in our code, this will come out as a list of lists. So actually we'll have a list of potential combinations. So we've got this square brackets is representing our outer list. It's one big list with lots of little lists inside of it. So our first combination is represented here, 0, 1, 2, 0, 1, 3, and then looking back, so 0, 2, 3, that is this combination. We've got Leafy Lane, we haven't got Cactus Heights, we've got Flower Pot, and we've got Sunny Mountain. And we can have the other. Well. And in fact, we won't actually write that ourselves, or we don't need to sit down and calculate them. We will get a function from Python to do this for us. So we'll get the combinations function from the itertools package via a custom function that we've written for you. So you can take this away and reuse it. Just gives you everything that we've just talked about in a nice output. All you need to pass in is how many facilities have I got, the number of candidate locations where facilities could be located. That might be that you've got 5 existing facilities and you want to drop them down to 4, or it could be that you've got 300 possible facilities, but you only want to actually place 10. So in that case, it would be 300 as your number of facilities, 10 as your number of clinics to place. Or in the first example where you had 5 clinics, that would be your n facilities is 5, and you want to drop it to 4. Okay, we only want to pass in p is equal to 4 number of clinics to place, and that will give you an output like this. How is it doing this? Well, first it's creating that array to represent all of the possible facilities based on the number of facilities that we pass in. So it uses NumPy to do this behind the scenes. So np.arange is NumPy array range. We are creating an array with the numbers, basically the number of facilities that we're passing in. So np.arange equals 4. Let's say we had 4 facilities, hypothetical facilities, then that means we need an array with 0, 1, 2, 3, just like we had a minute ago. 0, 1, 2, 3 were our clinics. So now NumPy has created this list for us as an array. Next, it works out all of the possible combinations and returns this as a special type of objects. So looking back at our code here, NPA range was our first line here. The data type, we're just saying, please give it as an integer number. We don't want floats. Decimal places don't make sense here. We just want an integer. So that's what np.uint8 is. It's just saying, please give it as an integer. And then what we can have is the section where we work out all of the possible combinations. So here it's just passing in to the combinations function from the itertools package, itertools, not quite sure how to pronounce that, but it's iterative tools. So we pass in the number of facility, or our facility array, and we pass in how many sites should be in each of the solutions we're passing in. So effectively what we're passing in to this combinations function is our array, including what data type it is, and how many sites we want to place in each case. What we then do is turn it into a slightly nicer output, because what we get out of that is this itertools.combinations attribute, this object. It's not much use to us like that. It's not given us a nice list of arrays that we're looking for. So we use a list comprehension. We're basically saying for every combination that is coming out of this this list of options, we want this. We want to get the possible combination out. So we get this as our output from this list comprehension. We're saying go through this combinations object and return each combination. That's what that A for A is. It's just return each without doing anything to it. Just give me the exact combination as you are storing it in your itertools combinations object. We get this as our output. Now notice that it's curly brackets rather than square brackets, or standard brackets rather than normal brackets around each of these. We want them as lists. That's just what we need going forward. So instead, or actually, we're going to turn it into an array, because an array is faster. Basically, when you get to these huge problems that you can theoretically tackle with this approach, then you will want NumPy arrays. Everything will just work that little bit faster. So this is just, as I say, to ensure things remain as speedy as possible. So what you get is just a list of NumPy arrays. NumPy arrays are basically a fancy list. So they're just a faster, kind of better list. Fundamentally, that is the same as this. We're still getting a list of lists containing combinations of facilities. Okay, so now it turns out someone forgot to tell us that there was actually a fifth practice that we needed to be considering, but they still just want to drop it down to 3 practices. So how many combinations exist at this point? I know that we can get tools to work it out for us, but I think it's useful to have a think about and start to understand how this number can increase. So I'd like also to give you a couple of minutes break from hearing my voice. Just work out every possible combination of these practices. How many do you think there are in total? You might find it useful to use some numeric IDs for these practices. So just grab a pen and paper, open a new Google Doc or something, just have a bit of a play around and try and work out all of the possible combinations of the practices. I'm interested in how many different combinations do you think there could be of 5 practices initially, but we only want 3 practices. So I'm just going to stop my video for a second. I'll catch up on the chat while you have a quick look at that. And we'll be back at probably, I'll give you until 11 minutes past, and then we will see what number you have come up with. So remembering we've got 5 practices, we want all the possible combinations of 3 practices. Right, hopefully you had a bit of chance to have a go at that and also to have a brief break from me talking at you. So just if anyone's got an answer, please pop it in the chat. How many possible combinations do you think there were? I will give you the answer in just a second. Got a couple coming through. Yeah, everyone's got it. 10 possible combinations. So this one isn't too hard. There's not too many possible combinations. Dan, I think I love Dan's answer. So we've got the answer is somewhere between 10 and 26.2 million, 27.6 million even. No, the answer is 10. So not too many possible combinations of these practices. So yeah, you can see that was probably a little bit of a pain to work out, and that was a relatively small problem. You can see why it's really useful to have a function that will work this out for us. So when we get to bigger numbers of combinations, I imagine you'd rather not have to work that out manually, especially what each combination is for, 100 possible sites and wanting 5 of them. So how big can the number of combinations get? So some of you I've seen already in the chat are starting to kind of bring up these formulas. We can use this formula below to work out the total number of possible combinations in a scenario where the order of options doesn't matter and you can't repeat options. So we can't have the same service appearing twice. That wouldn't make sense here. And like I said before, it doesn't matter which order we put the solutions in our output. There are different formulas for this. In this case, this exclamation mark isn't emphasizing things here. It's the mathematical symbol for what we call factorial. So if we have 5 options, that makes the top of this 5 factorial, 5 exclamation mark. So that's 5 times 4 times 3 times 2 times 1. That's all factorial means in this setting. So 2 factorial will just be 2 times 1, 3 factorial 3 times 2 times 1, and so on and so forth. So number of options, we've got 4 options here. We're selecting 3. This is 4 factorial on the top, 1 times 3 factorial on the bottom. So if we've got 4 options and we're selecting 3, this is 4. And we've got 4 possible combinations, as we showed in our first example. 5 options and selecting 3, we've got 10 possible outcomes, 10 possible combinations of solutions, as you all correctly worked out. But the number of combinations can get out of hand extremely quickly. If you're working in the level of a single trust or with some fairly centralized services, maybe at an ICB level, you'll probably be okay. But if I'm a national commissioner and I'm looking to close 1 of 30 services, there are 30 possible combinations. That sounds fine. If I want to close 2 of 30 services, then there are 435 possible combinations to evaluate. If I need to close 3 of those 30 services, there are suddenly 4,060 possible combinations to evaluate. 4 of those services, 27,000. 5 of those services, 142,000 possible combinations that we need to work with. If you've got 100 services and you want to close 5, so we've moved up the number of services, we're still only closing 5, there's something like 75 million possible combinations that we need to work out and evaluate. So it's going to take some time if we try and sit there and manually brute force all of those combinations. If we work out the average travel time for each one of those combinations, even just trying to store all of those results would take a ridiculous amount of computing space. So that this works for small scale problems. You have to start thinking a little bit more out of the box when you get to these big problems. And from this, I hope you can see that what looks like a small problem can become a very big problem very, very quickly. So there are ways to deal with these solutions. There are ways to brute force them, but it is quite a tricky area to wrap your head around. We will briefly cover this. Well, we won't cover it a bit later today. I will provide the additional slides. We're not going to have time to go through the concepts around this today. We won't go into detail in the course on how to go about this process. But we do find that people do find this useful for their projects sometimes. We had someone last year who was doing neonatal service locations at a fairly large scale. I think it was across the whole of the Northwest. So they needed to start using these more elaborate methods to be able to evaluate the problems without going through every single possible combination. So we do have materials available. If you want to do this in your own project, we absolutely can and will support you. And there are members of the HSMA community, like this person from last year, with experience in this area, if this is a route you need to go down over your, for your project. So all of that said, what we're going to focus on today is the kind of scale of problem where you can brute force it, where you have a small enough number of combinations and possibilities where you can actually get the output straight away just by going through every possible combination. And that can work really well. You know, as you saw, we talked about some of the likely sizes of combinations, and there are plenty of problems where you can just brute force it, even up to the scale of a couple of thousand. You know, these don't necessarily take that long to calculate. They don't necessarily take that much space to store. So you can, you know, brute force a relatively large problem. So what we need, we've been working through our sort of steps of what we need to be able to provide to do this problem. We know the combinations we want to test. We know how long it takes to get to each clinic location. That's what we were looking at last week, our LSOA, our travel matrices. Now, for our weighted travel times, we need some sort of demand figure. So chances are your demand isn't spread evenly across your potential service user catchment area. Maybe some LSOAs have more people of childbearing age, so your maternity and paediatric services would get more people from there. Maybe certain LSOAs have an older population, so certain kinds of services are going to be more centered around there. Maybe other LSOAs have a higher incidence of obesity, so you might have more demand for perhaps type 2 diabetes services or weight loss management clinics or something like a retinopathy clinic. So there's lots of different ways you might be kind of trying to work out your demand. As I say, not necessarily just historical demand, but bringing in this sort of this either what the situation is right now. And you could also provide, I saw in the chat someone asking about, you know, what about this in 5 years? Well, you could provide both. You could absolutely say, here's the situation right now. Here's the projected situation in 5 years. You know, quite often it is, I believe, either the sort of public health agencies or the ICBs who might have these sorts of projections. So if you're working at trust level, you might need to reach out to colleagues in other organisations to be able to get the best projections for the future. Some of it may also be available just online from the government type websites. But, you know, you can provide both. You can say this would be the best solution right now, but oh, wow, 5 years time, 10 years time, that wouldn't be a great combination of clinics. So again, your stakeholders can decide how much that matters. Do they want to sort of sacrifice the best possible solution now if the fifth best solution is going to be much better in 5 years time? And actually, maybe there's not that much difference between the two right now. So yeah, it's always coming down to what kind of decision support can you be providing people. So demand data, well, this can be formatted really quite simply. This is a lovely kind of data frame to be working with. All you want is that you're using the same level of location data in your travel matrix and your demand data frame. So you don't want LSOAs in your demand data frame and MSOAs in your travel data frame. They both need to be working at the same level of aggregation. And our LSOA data frame, our demand data frame even, will just have a column or an index for our LSOA names or codes. So and then we'll have a column for the demand. Like I say, I keep talking about demand. Doesn't have to be historical demand. It can be these projections. It can be some sort of calculation of, well, we've got 30,000, not 30,000, let's say 3,000 people in this LSOA, and we reckon that 5% of them will need to use the service. So that could be your demand, something like that instead. Or it could be, we reckon that there's 3,000 people in this LSOA, but this many of them are older, and this many of them we therefore expect to use the service, and that could be a demand. So demand is just a column containing some way of weighting your travel times in terms of the number of people who are likely to be accessing the service. And then we have our travel data frame from before. So we've got the LSOAs, we've got the possible site locations, and we've got the shortest travel time that we will be calculating on a sort of per combination basis. So as I say as well, you might be using those historic demand figures as your starting point, but you do need to consider, if you have areas with no historic demand, is this actually a realistic pattern, or is it just that the historic numbers are quite small and there's an element of chance coming into this? Or is there some pre-existing bias or issue with access that you might be perpetuating by using those historic figures? You know, it could be that the old services were terrible for public transport access, and therefore no one who needed to use public transport could ever get to them. And therefore you might have seen certain areas, certain LSOAs who just, had lower than expected figures or no access. And again, for services that aren't seeing a huge number of people, if you've only got, say, a year's worth of data that you're working from, then by chance you are likely to just have no demand from certain areas. So could you bring in more years? Could you explore what happens when you do just weight demand by the number of people in each LSOA? So this example here was weighted by historic clinic demand, and we saw that we had an average travel time of 15 minutes, and we had a lot of regions showing up as blank, effectively, that we just had we didn't provide a travel time, we didn't factor them into our analysis, because historically they didn't have any data, they didn't have any demand, so why would we include them? Well, actually, if we just averaged out, weighted by some sort of theoretical demand by LSOA instead, our average travel time jumps up, and potentially even our best solution changes quite significantly. So always just consider, when you're making these adjustments to what your demand figures might be, consider whether they're appropriate, sensible, transparent, and justifiable. Make it clear what data you've used and why you've done it, and make the limitations of your conclusions explicit. When we get to module 8 and start talking about Quarto and sort of literate programming, being able to weave together a report that has code outputs and text, this is a great way to be able to include this additional kind of information built in, written right in with your code, so it's clear as day and can't be missed. Or you can, you can bring it to the forefront, you can hide it away for people that do want additional information, but just make sure that it's clear, appropriate, and the next person that comes along across your analysis understands where those figures for demand are coming from. So we've got everything we need to feed in now. We've got travel times, we've got demand, and we've got geographic data, basically everything we need. The only thing now is a way to calculate it. So we want to give the weight to the travel time, the areas that have a higher demand. So we're going to write some code to do this. And the great news is, you'll be really pleased to know that we provide this code for you. You just need to be able to use it, but it's useful to understand what's going on so that you can tweak it and expand it yourself. We're going to want to reuse this quite a lot, actually. So basically, it makes sense to turn it into a class. We're going to give it some attributes. That's going to be our travel data frame and our demand data frame. And we're also going to give it a couple of different methods. We're going to give it a method to evaluate a solution. So when we pass in a subset of candidate locations, we're going to make it work out the smallest value location, the sort of minimum cost, that shortest weighted travel time. And we're also going to get it to return a data frame with all of this data in, so we can access it and reuse it. We're also going to get it to have some methods that will return basically some useful outputs. So the weighted average, the unweighted average, and the maximum travel time, so that we've got all of these to hand. So first, we're going to call this the facility location objective class. So we create a class. Remember, using the class keyword. This is what we're going to call it, and then we need a colon to say everything within here, indented, relates to this class. We're going to use the def init. So remember, this is 2 underscores init and 2 underscores. We pass in self, and then we pass in the things that we want to change, effectively, the things that we want when we set this up for a new facility location problem, the things that we might want to change. And we're making this quite flexible, so actually it can be used across lots of different problems, not just the example problem we're using today. But what we want to pass in is a demand data frame. So this is the one containing a column of LSOAs and a column of demand per row. So each, as you read across the row, you've just got one column, and that's, we have 25 people, or we're expecting 25 people from here, 5 people from this next LSOA, 30 from this next LSOA, and so on. The travel matrix is the data frame with the demand sources as rows and the potential service locations as columns for every possible location where you might place your sites. You've got each of those as a column, the places where people could be coming from as rows, and your travel cost as your cells. When you read across and down, that will be the travel time to that LSOA, to that site from that LSOA. In this, we're also just passing what's called a parameter called merge col. So this is going to be the name of the column that is consistent between our demand and travel data frames. We may need to do a little bit of pre-processing to make sure that there is a column that is named the same between our demand and travel data frames. And demand col is a string referring to the column that contains the demand value in the demand data frame. So it could be that our demand column is named number of patients or historical demand or hypothetical demand or whatever we've called it. We just need to tell this facility location objective what that is. And that just makes sure that this method, this class is as flexible as possible, that it allows reuse with different data sets rather than hard coding those data sets in. So every time you come to a facility location problem, you can just start with this and that's all you need. We've then got a method called evaluate solution, and what we pass into the evaluate solution is the list of potential sites we want to evaluate. What it does is it filters down the travel matrix to just include the sites that we want to look at right now. It works out the minimum cost, the minimum travel time across those facilities only. It looks at that and weights it by the, well, it doesn't weight it at this point, actually. It gives us a data frame that is the active facilities. It merges that with, it merges the demand and travel times into a single data frame, including that minimum travel time. And then it returns a data frame where actually so when we've used reset index here, all that's doing is going, I don't want my LSOA names or my MSOA names as an index. I want them as a column, just because it makes it a little bit easier to work with down the line. Finally, this one here generates solution metrics. Again, we pass in a list of sites in the form of their column indices. So for example, sites 145 or indices 145 would refer to sites 2, 5, and 6. Remember, Python is counting from 0. You've always got to kind of account for that jump. What this method does is it runs this previous method, evaluate solution. So it evaluates the solution for us, and it returns a number of metrics relating to the problem. So it returns this weighted average. It weights the average. It weights the travel times by the demand column. It returns an unweighted average as well. So actually, if you do strip the demand out of this, what's the average? And it also returns the max travel time for any LSOA in this particular setup configuration of sites. And it returns us a nice dictionary. This dictionary contains what sites are in there. It returns the names of the sites, if there is a site name. It returns the weighted average. It returns the unweighted average. It returns the maximum travel time, and it returns that data frame that we created here as well. Why is that so useful? It's really handy because then we can pull out the stuff from this class method, and we can turn that into our plots of travel times. So this, as I say, is all provided for you. You don't need to worry too much about the intricacies of what it's doing. You'll only need to come to that if you're actually trying to modify it potentially, but it's useful to have a broad overview of what this code is doing, but this is already in the notebook for today. What you will need to do is use this facility location objective. So in this case, I'm working with some location problems in Brighton. I've got, I think, 6 possible sites. And what I want to pass in, I want to create a facility location objective with the demand in Brighton. So this is my demand data frame. I've got a series of LSOA names and I've got the demand. I've then got a series of, I've got the Brighton travel, the travel matrix. So I've got rows with the LSOA names. I've got columns with the sites, and each one of these is a travel time. In this case, in seconds. That's why it looks so long. My merge column is my LSOA. My demand column is called demand. So my merge column, in this case, before I passed it in, each one had a column called LSOA, and my demand column is called demand. They then become attributes of our class. So I've created an instance of our facility location objective class called location problem Brighton. I've then said, I want to look at the travel matrix that I've created in here. I want to look at the demand matrix that's attached to this facility location objective. It's all neatly in the same place, and we can pull out both the data that we passed in, and in a minute, we'll be able to pull out the solutions. So if I just run the evaluate solution method, and I pass in a list of possible sites. So I've said I want site index 0, 1, and 2. That's looked at just sites, what are numbered 1, 2, and 3, but effectively they're 0, 1, 2. Remember, Python's counting from 0. It's looked at this matrix here, this travel matrix, and gone, right, this is column 0, site 1, this is column 1, site 2, and this is column 3, index 2, site 3. So it's limited the sites, it's worked out the minimum cost by reading across from these. So now we can start to pass in a range of solutions, including with different numbers of sites. It's completely flexible. As long as the number of sites you're passing in is lower than the number of sites that exist, then it will work. You can't pass in more sites than exist. And you can see here as we pass in different combinations of sites, the available sites are changing. We can then return the metrics for the solutions in each case. So we've got the location problems in Brighton. We're generating the solution metrics. And what we get is this output. We get a list. We said we wanted sites 0, 1, and 2. So we've got site indices 0, 1, and 2. It's returned the column names. So actually, maybe our sites are called something like Sunny Hills Practice, Mountain View Road Practice, etc. That's as long as that's what our column names are. So these don't have to be site 1, site 2, site 3. They could be the name. They could be the postcode of that site as well. Anything that helps identify what that site is. So site names, it's pulled those out for us as well. It's calculated the weighted average. In this case, it's 388 seconds because this particular travel time API I've pulled back from gives me results in seconds. It's given me the unweighted average, and it's also given me the max possible travel time. And finally, it's given me an entire pandas data frame stored within our dictionary that I can then pull out. And this looks very similar to the data frames we were using to plot the travel times previously. We can also access easily a single metric like the weighted average travel time. So I've created this solution object, which is just the location problem, the output of the generate solution metrics method, and I've passed in a series, a list of the possible combinations. And then by using this to index our data frame, I've pulled out just the weighted average. So I could put that in line in a report, something like that. I could say the best possible solution has solution weighted average, and that's the output that we'll get. You'll love Quarto for that when we get to it, for being able to put little bits of your code straight into the text outputs of your reports. So now we go back to our code from all the way back at the beginning, this all combinations function that calculates it gives us an array of arrays for every single possible combination. So we've created a list of all of the possible combinations. That's what this looked like. And now we can start to loop through every possible combination and save the outputs. So we make an empty list for every possible solution in the possible combinations. We basically do this bit where we create the location problem. We've created the location problem a moment ago. We generate the solution metrics. We pass in one of these possible solutions, and it starts to build us up a collection of all of these metrics, all of these data frames for every possible solution, every possible one of these combinations. And even better than that, all we have to do is do pd.dataframe, and all of our outputs turn into a table that we can use. So now we have a data frame that goes through and has all of the site indices, all of the possible indices, what these site names actually are, and then starts to give us things like the weighted average for each of these solutions, the unweighted average, and so on. And then it's really easy to find the best combinations. We can just sort our data frame by whether we're interested in the weighted average, the unweighted average, the maximum travel time. We sort the values, and we can also do something to pretty it up a bit. We can round all of the numeric columns by to one decimal place. So you can see that's a little bit nicer to work with than the previous example where we had all of these decimal places. All we need to do is say, please round this data frame. And now, since we stored these combinations in our data frame, we can pull this out by chaining together a few steps. We can put this all together into a plot in a second. So what we've done here is we've gone, I want to sort, I want to make a data frame of my outputs. So again, this combination, all of these possible outputs, I want to sort these values by the weighted average. I want to take the best one. So I've sorted it so that the best example is at the top, the shortest weighted average travel time. I then just want the first one. So this head method, we've used head before to demonstrate what the, to pull out a sample, like the sort of top 5 rows of our data frame, but we can use it to just bring out the first data frame as well. I then want to pull out the site names, and I just want that as a value. I don't want the column, I want just what's in that cell, effectively. So I've gone, get me a data frame, sort it so that I've got the best solution at the top, just pull back the best solution. I'm only interested in the names, and I just want what names they are. So we now know that our best solution, if we want to pass that on to someone, is site 1, site 3, site 4, and site 5. And then we can elaborate, we can take this to the next step, which is building in the travel time, the best possible travel time, and the maps that we were creating before. So again, we can just pull out the best possible solution. We want the best solution data frame. So again, we're creating a data frame of our outputs where we've gone through every single possible combination. In this case, I've sorted it again by the weighted average, and I've said the head. This time, I just want the problem data frame. I want the data frame of all of the travel times for this particular solution that I've stored. Now, this dot value 0, don't worry too much about what that means. Just remember that that means you will be pulling out the data frame in a format that you can use. So that will be given, that's just a little thing that is worth remembering when you're accessing bits of a data frame. If I just pulled back this here, just the problem data frame column, what I would effectively be pulling back is a column of a pandas data frame. And if I try to do something else with it, it still thinks it's, it gets a little bit complicated. Just pull out the values from that cell. Effectively, you're just saying, I want to reach into that data frame, pull out just that. And this little index of 0, just make sure you are only pulling out the exact data frame. So like before, we're going to make sure that we've got our travel time boundaries. We're going to go through the nearest site travel time and work out the minimum cost, in this case in minutes. We're simplifying it down to minutes. We're then plotting. I will be giving you time as well. If you didn't finish the travel time plotting exercise from last week, there will be plenty of time to carry on going through that first before we go through into the next exercise. I won't go through the exact details of all of this because I think you're all probably getting quite knackered of hearing me talk, but come back to here, come back to this cell to look at this slide, even to look at the plotting code. But effectively, what this just means is, as I say, we're pulling out the data frame for the best solution. This line just ensures that when we're pulling out the sites to plot the individual sites on top of our travel data frame here. So you can see we've just got site 1, site 4, site 3, and site 5. Haven't got site 2, haven't got site 6. So we just want to make sure when we're plotting our points on top of our map, we're only pulling back the ones that are relevant for this solution. That's what this second line here is doing. And then it really doesn't take much effort at all to turn this into a map with weighted travel times for every possible solution. And you can see that as we read across here, it's ordered by the best possible travel time. They're not just in a random order. They are starting with the best solution up here and what is theoretically the worst solution over here. So we're just iterating through our data frame of solutions. We're pulling out one row at a time, and then we're using this plot code that we've used before, exactly the same plot code, but we're just working through. So again, subplots, there'll be plenty of time to practice this in the exercise. Don't worry if you don't get onto this. If you can just plot the best solution for now, that's all that needs to, that's all we're aiming for today. And as I say, benefit of saving all these different things is we can access things like the weighted average travel time for each solution and pop that into our title. You might want to consider ways to display the outputs in other ways too. So actually here we've got the possible site combinations as in this bar plot, and actually the weighted average travel time is being shown in minutes. We've ordered by the shortest weighted average travel time up to the highest, and that just gives people a very quick overview of the magnitude of difference between different solutions. We're using the Plotly library here. Plotly is a lovely interactive plotting library that allows you to create plots very simply. So here, all we've had to say is, I want a bar chart. I want my y-axis to be my site names. I want my x-axis to be my weighted travel time in minutes. And I'm going to give it a title. So it's very simple compared to what you might be getting used to with Matplotlib. Plotly can give you a really nice, easy way to make common chart types like bars, scatter, etc. And I have shared a little bit of information about Plotly in the HSMA Cafe channel, I believe. So just before we go on to the exercise, 5 more minutes, I'm going to give you a flavour of how we would go about tackling these more complex ones, the ones with very high numbers of solutions. am I going to do this now? I'm going to come back to this. I think you could probably all do with a break. So we're going to have a 10-minute break now, and then we're going to work on this exercise. You're going to have potentially up to 75 minutes. I'm going to give you a really nice long period of time to work on this. And potentially, if you didn't finish the travel time plotting exercise from last week, if your group didn't have time to get through all of that, start with that. I would recommend just give yourself a bit of time to get back into the swing of plotting travel times, and then go on to this facility location problem notebook. The thing to note as well about the the challenge in this notebook as well, is that if you open this up, when you get to the challenge, there is a section on calculating some of your own travel times. Now, this is what we would have done at the end of last week, but I wanted to make sure we had time to really go through these facility location problems, because this is kind of what the module builds up to. This is the key part of this module. So when you get to that section of the exercise, you may not know how to calculate your own travel times. I will make sure that there is a link to the slides that relate to that, and the geographic book that also goes through this. So if you in your group get to that, try and have a work through those slides yourself, try and understand what's going on, try and teach other members of the group, just have a bit of a play around with trying to work out how you would pull back your own travel times. If we get time towards the end, we'll kind of judge how everything's going. I may go through the theory of how you calculate these travel times later on in the session. But for now, I just want everyone to have a chance to work through these facility location problems. The code, so I've gone really into the detail of why we're doing everything, how we're doing everything. When you actually get to the code, as I say, the facility location objective code is already provided. So it hopefully won't be as complex as it looks to actually start calculating some of these outputs for yourself. So I'm going to leave it there for now. As I say, 10-minute break, but first, do we have any questions? I don't think we have anything here that wasn't covered before. Dan, anything you've spotted that that either you haven't been able to respond to, or anything that I haven't responded to as well?
No, I think you covered everything, Sam. I think I've managed to answer most things, and anything I didn't, you subsequently covered. So I haven't spotted anything else.
Great. Thanks, Dan. Cool. Right. I'm going to open up the breakout rooms then, but please do take at least a 10-minute break before coming back. And I will post in the chat how long it's going to be before we regroup. I think it will be roughly around about probably bring you back around 12 o'clock, just so that we can have a chance to go through this travel time stuff as a group. But it may be a bit sooner, depending on if I go around the groups and find everyone's actually just sped through this whole thing, then I'll bring you back a bit earlier. Right, okay, see you in a bit. Hi everyone. So I've brought you back now. I know that there wasn't quite enough time for everyone to finish the exercise. The solutions will go out. I'll share them over lunch, but they will be available. But I saw that most of you had got through the first section. You'd managed to use the facility location objective code. You'd managed to get your outputs, and you were mostly starting to work on the visualization section. So I want to make sure we've got a chance to cover a couple of other key bits in the remaining time as a lecture, and also kind of signpost you to some of the stuff that we would have covered on using travel time APIs to get your own travel time data for both walking, cycling, possibly even public transport, etc., so that you're not sort of just confined to the travel time example matrices that we've given you for the course. Before I do kick off with that, I do just want to recognise that, you know, this is difficult stuff, what we've built up to over the course of 4 quite short sessions. We've done a lot with pandas. You haven't had much chance to practice pandas before. We've introduced geopandas as well, you know, which is another layer of complexity. You know, this hopefully will all feed into your confidence and understanding of pandas as a package as well, which will be very useful for other stuff that you work on. But also just the general facility location optimization stuff. This is taught on master's levels courses. You know, we keep saying that some of this is master's level. This really is. And the bits that we're about to cover, just on the concepts of, you know, solving very large scale problems, that is Masters Plus level. So don't worry if you don't get it all, but what we want to equip you with is a basic understanding of the concepts and the possibilities and a little bit of boilerplate code that you will understand enough to be able to adapt it if this is something that you want to work on for your project. And as I said, you may then spend 9 months effectively doing what we did today, taking this kind of problem and starting to, you might do a couple more outputs, you might come up with a web app to go with it, but at the core of it, what you may be doing is the kind of code we've done today, and you'll be building on that for potentially weeks and months, having time for it to really start to make sense. So it won't all make sense at the end of the day. Code rarely does. Honestly, it's, there is a lot to take in. So if you're still kind of going, I don't really feel that confident with this, don't panic. We won't be sort of testing you on it in great depth. There won't be an assessment at the end where we say, right, you need to go away and, conduct a full geographic optimization, problem right now, no reference to the code, etc. Nothing like that will ever happen on this course. That's, it's no use to anyone, but just hopefully this gives you a starting point for any further journeys you want to do with geographic optimization work. I'm just going to make sure I've got the chat open as well. So, oh, Dan has just said, that's my plan for the test out the window. I'm sure all of you are very grateful that that is not the format the test will be taking. We're far more interested in your sort of, code is no good to anyone. You're never going to be coding in a vacuum. You're never going to be coding without access to your historical code. You'll be adapting the code that we provide. You'll be adapting code you find elsewhere, and you will be adding your own flavor to it and your own spin. And eventually you might be writing it all from scratch, but that is not the goal right now. Why start from scratch when it's a solved problem? But if you understand what the code is doing, even to the point where you begin to understand how to break down what the code is doing, that is far more valuable. So, going to quickly go through some stuff. We're not going to actually do any more coding exercises on geographic stuff. You'll be pleased to know, we might return to it in the web app stuff just so you can see how nice it can be within a web app, but we won't do any more actual coding today. So you can just sort of sit back and enjoy hearing about what we do when we make these problems more complex and how you might start to pull back your own travel matrices. When we get to the really, really complex algorithms, like what we call genetic algorithms and evolutionary algorithms, which are sort of inspired by biology as a way to solve these huge impossible problems, the ones with 74 million possible combinations of sites, for example. Before we try that, we can do what we call a heuristic. Now, this is just any approach to a problem that is not a perfect solution. It's not fully optimized. It's not perfect. It's pretty good. It's a pretty good way of coming up with a reasonable solution to a large problem. There's no guarantee that this solution is going to be actually the optimal one, or even necessarily that close to being optimal, but it will be better than just, well, you in a size of problem where you can't brute force it, better than just working through the first 1,000 that you possibly can. This will be probably a better way to go about it. So the simplest way to deal with these very, very big problems is to do a series of random solutions. We might not find the perfect solution, but we will probably find a good enough one. So what we then define, instead of the complete possible set of all possible outputs, we keep generating random solutions. You may have noticed, or you will have noticed in the code, that there was a bit where we generated just one random solution. Well, we'll just keep generating random solutions. We'll have sites 0, 1, 3, then we might, or 0, 1, 3, 5, 7, 9, 0, 1, 3, 5, 7, 10, and then it might be 3, 2, 4, 5, 6. It's going to be completely randomized each time from scratch. It's just going to be the right number of sites that we're interested in. We'll set a maximum number of solutions that we'll try. So we might say, I just want you to try 10 solutions. More likely, you'll probably try 1,000. You might just actually kind of go, well, I'm going to leave this running overnight. Maybe I'll try 30,000 solutions. But in those very large solution spaces, taking random solutions, taking enough random solutions, you're probably going to find something that's pretty decent as a solution. And what we'll do is we'll keep track of the best solution we've found so far as we go along. If we try to do exactly what we've done here and try to store 30,000 theoretical data frames, that's not probably going to be our computers probably aren't going to like us very much. We may want to store maybe the top 10 instead. There are some different ways we could go about this, but for now, for the sake of simplicity, we'll just keep track of the best solution we've found so far. So let's say we've got a sexual health clinic data set, 306 possible clinic locations. They want to place 20 clinics. That gives us, I think 11 nonillion. I'm glad I gave myself that that reference, otherwise I have no idea how to say that number. So a very, very large and impossible number of solutions to evaluate. So what we do, as I say, is we store the best cost and we just keep asking for random solutions. We evaluate the random solutions and then we generate another random solution, evaluate that, another random solution, evaluate that, and so on. At the end of this, so when we've started this particular random restarts function, we've created an empty variable effectively to store the best cost. So this also came up in one of the questions, why do we talk about costs? It might not always be travel times that we're working with. It might, and also historically, when we've talked about travel times, the general terminology is just travel costs. But the way I think about it, the way I can't call it costs, is because you might fill your travel matrix with, CO2 emissions. You might extrapolate from the travel costs and the likely transport to be CO2 emissions. It might be that you're talking about the distance instead. And when we go on to, in some of the master classes, talking about multi-objective optimization, cost makes sense because you haven't got a single sort of defined metric that you're trying to minimize. It's not just travel time, it might be multiple things as well. So minimizing the cost makes sense. But anyway, best cost, best solution. So what is the combination of site indices that is the best solution we've found so far? And also, I've also made a list here called solution progress and empty list, where for the number of iterations I'm going to try out, I am going to store the actual, I'm going to store how well the solution, how the cost of the best solution has changed over time, just so we can see how that's changed. So what we do is we set how many iterations we want to go through, how many solutions do we want to try, and for I in range, max iteration. So for solution 0, solution 1, solution 2, etc. Here would go up to effectively 1,000 iterations through. I is just how many, is this solution number 1, solution number 2, solution number 3. We don't pass in a random seed here. So in the code, in the examples, in the exercise, you passed in a random seed. So you would always get the same reproducible output. We set the seed to 42. That just means that the computer will always give you the same random output. We don't want to do that here, or we'd be checking the same solution 1,000 times, which is no use to anyone. But what we do then is we use our same facility location object, we generate solution metrics, and we pull out the weighted average. What we then check is whether the cost we've just found is better than the best cost we've previously recorded. So is it lower? If it is, we overwrite the best cost and we actually store what that best solution is, which is where we had this none type object at the top. And then we just also, to our solution progress list, we go, right, this is iteration 1. And at this point, the best cost I had was, average weighted travel time of 30 minutes. On solution 500, we actually managed to find a better one just purely by chance. And then the best cost was changed, and so on and so forth. So what I'm going to do is I'm going to show you a visualization of that. So here we can see how the solution finding progressed over time. We had 1,000 iterations, and we started the first solution, the weighted average travel time was 8.5 minutes. After a couple of solutions, maybe solution 2 or 3, the next best travel time we found was actually 7.3 minutes, weighted average travel time for that combination of clinics. About 50 solutions in, the best travel time we found was 6.5. And you can see then we had this very rapid period where we found better and better solutions, and then we didn't find any better solutions for a while. We got to iteration about 210 before we had another significant drop. Iteration 600 before we got down to 6 minutes weighted travel time. And by the time we reached about solution 650, we went another couple of hundred solutions without finding anything better. Scale this up to 10,000 iterations, 100,000 iterations, 1 million iterations. To be honest, after 1 million iterations, the best weighted travel time solution I'd found was 5.3 minutes. Compare that to 1,000 iterations, 6 minutes. You know, you might not be finding absolutely astronomical leaps in terms of the best possible combination, but it will be most likely better the more iterations you run it for. And you may get really lucky. You may find the optimal solution on run one. Extremely unlikely, 1 in 11 nonillion chance, but you know it's there. It is possible. So to take that even further, if we wanted to actually have a better chance of finding the optimal solutions, we can use what are called evolutionary algorithms. These incorporate sort of standard evolutionary algorithms and what we call genetic algorithms. We're moving into the realm of bio-inspired computing. We're sort of breeding pools of solutions to try and gradually, iteratively move towards the best possible solution that exists. And we also can use something called linear programming, which is complex, and one of the limitations seems to be that it's very difficult to get back more than just the best solution. So where we were talking about all that stuff with stakeholders and how valuable it can be to provide them with a series of possible solutions, linear programming generally doesn't allow that, but evolutionary algorithms and genetic algorithms do. So we won't cover this today. I won't go into any detail about how these work, but there are slides available. There are some optional exercises available on this, and it is something, as I say, that you may need to consider if you're working with a very large-scale optimization problem in your project. And Dan and I are happy to support with that and put you in touch with people within the HSMA community who have done that in their own projects. So there's some links to those slides on this, and I will provide some additional links post this session in the Central Plaza channel. There are also going to be some other additional masterclasses, I hope. So what Dan and I, or what's been done in previous years, is during phase 2, anything that we wanted to try out, brand new content, you know, right at the cutting edge of what the team are doing, and also things that were just impossible to fit into the main training. So we run these as masterclasses. They are optional sessions that will be recorded, but they run during the project phase of the program. We are hoping to provide additional sessions on geostatistics. So this is mostly written, actually. You'll be very pleased to know I had originally planned to include it in what we've learned in these last 4 sessions. That was a little bit ambitious. But geostatistics, we've got basically another 2 to 3 hours on that, of finding hotspots, cold spots, and outliers. So starting to look at patterns at either, you know, we can go a full UK level, we can go a smaller level, and starting to identify those areas that are unusual. The main law of geography is that things that are near to each other are just more similar to each other by default. That's just how, you know, geography tends to work. But where is that pattern not holding? Where are we unusual? Where are we finding real regions of extreme high activity, extreme low activity, or regions of low activity that are surrounded by a region of high activity and unusual in that way? So you can start to apply some statistical rigor to your geographic outputs. This can take you another level beyond just being able to provide maps of activity and maps of unusual areas, or trying to identify unusual areas. This will really help you to work out what is unusual and whether it matters. We'll also have hopefully a masterclass on what we call multi-objective optimization problems. So this is where we're starting to try and balance different conflicting requirements. So actually, if we wanted to look at something like the number of you know, we want to minimize the number of clinics while also maximizing the number of, you know, maximizing the number of people attending each clinic, but we don't want to go over an average estimated demand of a certain, you know, let's say 2,000 people per year going to this clinic. But we don't want less than 600, but we also want to minimize the average travel time that people, you know, will be spending. So that's where we're starting to get to these really complex multiple objectives trying to be optimized at once. So we will hopefully have a masterclass on that as well. So that's the end of this section.